Good evening, everyone. Welcome to this NPTEL course on hydraulic engineering, week 11 live session. So, this live session was basically related to computational fluid dynamics. And if you have gone through the lectures, you must have understood what is the necessity or what is the importance of CFD, that is computational fluid dynamics. See, whenever we go for any sort of analysis or investigation of any complicated fluid flow problem, the two traditional approaches are: one is your mathematical exploration, okay, and the second one is your experimental exploration, okay. So this CFD is nothing but it is a approach which lies in between this mathematical approach, where we tend to find the exact solution for the governing differential equations of the flow problem that you are studying. And in the experimental approach, what we do, we try to replicate, okay, you make a model of the actual prototype of the actual scenario in a lab or in a controlled environment, and you try to predict the results. CFD, which is the approach of numerical experiments, okay. So what we do in case of CFD, we try to solve the governing equations of fluid flow problems by using numerical methods, okay. So we use numerical methods, and if you have already gone through the lectures, then you must have understood that uh, this particular the traditional techniques available for solving the governing differential equations are FDM, that is finite difference method. Then there is FVM, which is finite volume method, and we have FEM, okay, which is the finite element method. So these are the traditional methods which are available. Apart from these, there are a lot more methods. For example, spectral element method, boundary element method. Then we have some meshless techniques like SPH, which is smooth particle hydrodynamics. Then moving particle implicit method, okay. So there are moving particle semi MPS, moving particle semi implicit method. So like this, there are different methods which are available, okay. So uh, if we focus only on the content of this course, then you must have understood that the discussion was solely restricted to your finite difference method, okay. So this finite difference method, finite volume method, or finite element method are basically methods which can solve any general partial differential equation or ordinary differential equation. But in computational fluid dynamics, we basically see how these methods or numerical approaches are being applied to solve the governing equations of fluid flow problems. So in general, we basically apply this equation for solving Navier-Stokes equation, okay. For incompressible fluid flow problem, it is the incompressible Navier-Stokes equation along with the continuity equation. So this is what this week's lecture was related to. So without see the content of the lecture is basically, if you have seen, you must have understood that you need to practice some problems, and it will be far better if you try to solve some problems by writing your own computer codes, maybe in some easy interpreted language like MATLAB or Octave or Scilab or maybe Python, okay, in order to develop the idea or the mathematical reasoning behind these techniques, okay. So we'll try to take up some similar exercises for today's session. Let's see. So this is the first problem. You have to write down the two-dimensional momentum equation for unsteady incompressible flow. So at this particular stage, I don't think we need to spend too much time on this, because you have already seen what is momentum equation. So basically you need to write the unsteady, two-dimensional unsteady momentum equation. So all of you just take 2 minutes and try to write the answer or the equation, two-dimensional momentum equation or the Navier-Stokes equation for unsteady flow. So I think that you have already written the equation, but just let me write the equation. So if it is two dimensional, let us consider that the flow is taking place along xy direction only, so there will be no, the z component will be missing. Okay, so the x momentum equation becomes del t of rho u, the general form. Okay, del x of rho u plus del y of rho u v. Okay, that's it. Because we are not considering the three dimensions, we are only considering the two dimensions. Minus of del p by del x plus mu del to u. Okay, and if there is some body force, then that body force component will be there, but let us say there is no body force. Now here this del operator is what? Del to the Laplacian operator. Basically, since it is two dimensional flow, it will be del to del x square plus del to del y square. Okay, similarly for your y momentum equation, what we have got? We have got del t of rho v plus del x of rho uv plus del y of rho vv. Okay, del y of rho vv minus of del p by del y plus mu del to v. Okay, so this is the answer basically. So you need to write the two-dimensional momentum equation for unsteady incompressible flow. Okay, this is the answer. Now let's move to the next question. Define what is meant by the statement that the flow is incompressible, and to what does the continuity equation reduce in incompressible flow. Okay, so what do you mean by incompressible flow? Okay, when we say that the flow is incompressible, we basically means that density is constant. Okay, now if density is constant, then if you write the general continuity equation del rho by del t, okay, del rho by del t plus del rho by del t plus del x of rho u plus del y of rho v plus what will be there? Del z of rho w equal to 0. So this is the general continuity equation. Now if rho is constant, then this part will become 0. All these rho are constant, so they will come out of differentiation, and effectively you will be left with del u del x plus del v del y plus del w del z equal to 0, or in vector notation del dot v will be equal to 0. Now what is this? This is basically what? Del u del x, del v del y, del w del z are what? This basically represents, sorry, this basically represents what? This represents the rate of this, the summation of these three terms represent the rate of volumetric strain. Okay, this represents the rate of volumetric strain, and if the rate of volumetric strain is equal to 0, so this is basically epsilon xx plus epsilon yy plus epsilon zz equal to 0. So it means that what? There is no strain, means there is no linear deformation along x, y or z direction. So that again means it is something which you cannot compress, and hence it is incompressible. So the continuity equation reduces to the form that the divergence of velocity is equal to 0 for an incompressible flow. Okay, Okay, this problem, now from this point onwards we'll try to see that what is the exact application of the finite difference method and all. So let a function be fx equal to x square. You have to find the backward and central difference approximation of del f by del x at x equal to 4 when you have chosen delta x to be 0 0.1, 0 0.05 and 0 0.01 and compare them with exact results. So please try this problem. In the meantime, let me get my calculator so that we can solve this problem together. Okay, we can discuss this problem together, and you try to appreciate the uh, this numerical approximation technique of finite difference method. Okay, so let's see what can be done. So first of all, the function that is given to you is the function that is given to you is fx equal to x square. Okay, now if you find del f by del x, okay, if you find del f by del x, then what will be del f by del x? Del f by del x, which is equivalent to df by dx because it is a single variable function, so it will be twice x. Okay, and you need to compute the value at x equal to 4. So del f by del x at x equal to 4 will be 2 into 4 equal to 8. So this is the exact answer. Okay, now we'll try to see if we try to apply the finite difference method. If we try to apply the finite difference method using different values of delta x, using different values of delta x, what will be the approximate values of this delta f by delta x at x equal to 4. Okay, you have to find the backward as well as the central difference. Okay, so for backward difference, say there is a function f, so f of x plus delta x will be what? It will be f of x plus delta x f dash x delta x square by factorial to f double dash x. So this is basically the Taylor series expansion of a function f of x around a point x in the positive as well as negative direction if it is if you take a length of around delta x and delta x. Okay, now if we use plus, there will be some other terms. Okay, now if this is denoted as f of I plus 1, then it is f of I plus delta x del f by del x because it is f dash x delta x square by factorial 2 del 2f del x square plus dot dot dot. Okay, from here if we ignore the higher order terms, and why this ignoring is possible, it is possible if we consider that the value of the delta x is very small, so we can ignore. Then delta f by delta x will be f I plus 1 minus f of I divided by delta x. Okay, so this is what you are getting from finite difference. Sorry, yeah, this is what you are getting from forward difference. Now let me preserve this equations. So delta f by delta x from forward difference is f of I plus 1 minus f of I divided by delta x. Okay, now if you write in terms of backward difference, what will you get? So for backward difference, f I minus 1 will be f of I minus delta x del f del x plus delta x square by factorial 2 del 2f del x square, so on so forth. Okay, so if you again ignore this higher order terms, then del f by del x will be f I minus f of I minus 1 divided by delta x. So from backward difference consideration, delta f by delta x will be equal to f I minus f I minus 1 divided by delta x. Okay, now the last part is back. Okay, so forward difference was not required for this problem, but since we are doing the exercise of finding the central difference approximation, so there automatically will be requiring. So let me write directly. This is for forward difference, this is for backward difference, and then we have one more which is the central difference. Okay, so how will you find that for the central difference? So let us redo this exercise with a different color ink, of course. So f I plus 1 is f of I plus delta x del f by del x plus delta x square by factorial 2 del 2f del x square plus so forth, so on. F I minus 1 is equal to f of I minus delta x del f by del x plus delta x square by factorial 2 del 2f del x square minus, like this it will continue. Now see, we want the approximation for delta f by delta x. So if we simply add these two, then the second term will get cancelled because the same quantity, only the signs are different, so it will get cancelled. So in order to preserve these two terms, what we need to do is we need to subtract f of I minus 1 from f of I. So if we subtract, what will you get? F I plus 1 minus f of I minus 1. These two terms will get cancelled. Twice delta x del f del x, again these two terms will get cancelled again twice. So we are neglecting the higher order terms. So from here delta f by delta x will be equal to f I plus 1 minus f I minus 1 divided by twice delta x. So this is the central difference. So from central difference what we are getting? We are getting that delta f by delta x is equal to f I plus 1 minus f I minus 1 divided by twice delta x. Okay, so this is we are getting from central difference. Now we will try to apply this. Okay, let us take the example of say x equal to 0.1, the first case. I will be describing only the first case. For x equal to delta x equal to 0.05 and 0.01, you please practice. Okay, so when delta x is equal to 0.1, what is f of I? F of I is nothing but twice x. F of I plus 1 is twice of x plus delta x, and f of I minus 1 is twice of x minus sorry f of I is x square, f of I plus 1 is x plus delta x whole square, and f of I minus 1 is x minus delta x whole square. Okay, so let us go for the backward difference. So for backward difference it is x square minus x minus delta x whole square divided by divided by delta x. So this is for backward difference. Okay, so x square minus delta x whole square plus twice x delta x divided by delta x. So these two terms will get cancelled out. We'll be left with twice x minus delta x only. Okay, so twice, see, actual result was twice x, but now we are getting an error of twice x minus delta x. So you can find the numerical value. The value of delta x is known to you, the value of x is also known to you. Now if we see, the actual answer is twice x, but when you are computing this using finite difference method and following backward difference, you are getting an error of minus delta x, means from the actual value the value will be deficient by an amount of delta x. Okay, now let us look at central difference. So for central difference it is f I plus 1. So f I plus 1 is x plus delta x whole square, f I minus 1 x minus delta x whole square divided by twice delta x. Let us see, x square plus delta x square plus twice x delta x minus x square minus delta x square plus twice x delta x, okay, divided by twice delta x. So these two will cancelled out. So 4x delta x divided by twice delta x. So delta x. So see, for central difference you are getting the exact answer, which is twice x. Okay, so why this is happening? Because of the order. What is the order of the central difference? The order of the central difference is delta x cube. And what was the order of the backward difference? For the backward difference the order is delta x square. So that is the reason. Okay, so similarly you try for other problems, you find the numerical value. Okay, now consider this continuity equation, del u del x plus del v. So two dimensional continuity equation for unsteady incompressible flow. Central difference approximation of this equation, and we have to check whether this finite difference approximation or the finite difference equation is consistent or not. Okay, so let us see. So what is the equation? Del u del x plus del v del y equal to 0. So here you have to remember that u, say at if at a coordinate point denoted by x, y, the value of u is say ij, where I stands for x, j stands for y. Similarly, vij, where I stands for x and j stands for y. Now what you have to write it, you have to write the central difference approximation. Okay, so just the exercise we have done right now, we can write directly that del u by del x, okay, can be written as u I plus 1 j minus u I minus 1 j divided by twice delta x, and del v by del y can be written as v I j plus 1 minus v I j minus 1 divided by twice delta y. Okay, so what will be the central difference approximation? The central difference approximation will be u I plus 1 j minus u I minus 1 j divided by twice delta x plus v I j plus 1 minus v I j minus 1 divided by twice delta y is equal to 0. Okay, so this is the approximation, but the next part is important. Why next part is important? You have to check whether this central difference uh yeah, what was the question? Whether the FD, that difference equation that we have written, this particular equation, whether it is consistent or not. So what is the meaning of consistency? See here, because of the Taylor series approximation, what has happened? Because of the Taylor series approximation, what has happened? uh, See, this was our actual partial differential equation, delta u del x plus del v del y equal to 0, and based on our Taylor series approximation we have written this as the difference equation. Okay, so partial differential equation, it can be written like this, is equal to FDE, that is the difference equation, finite difference equation. Just one second. Charge. Yeah, plus the truncation error. Okay, now by consistency we say that an FD is consistent, okay, as when this value of delta x and delta y, means as mesh size tends to 0, mesh size become fine, then your FDE moves towards PDE, means when, see, PDE is equal to FDE plus truncation error. Now if you, a system of FDE, means the difference equation is said to be consistent if you make the mesh finer, means if you reduce the size of delta x and delta y, then what should happen? Then this should approach the actual, this should approach the actual, this should approach the actual partial differential equation. Okay, that is the meaning of consistency. Okay, so please try and tell me whether it is consistent or not. Please remember that there are some other terms on this side, plus or means I'm just relatively writing plus size, which you have neglected. But if you are making the mesh finer, you consider all those terms and tell whether it is. See, an easy way of doing this is, see, your PDE is FDE plus DE, right? So it means that truncation error is equal to PDE minus FDE. Okay, your truncation error is PDE minus FDE. So if your truncation error is PD minus FDE, it means that as your truncation error tends to 0, your PD minus FD should tends to 0. Based on what? Based on this delta x, delta y, and if it is a time marching problem, then delta t. Okay, so that you check, and if you check, you will definitely find that this is consistent. You will definitely find that this is consistent. Now, an insulated rod. Let's move to the next problem. Now, this is the actual problem, and for this last problem, I would suggest all of you that I will show you how to formulate the finite difference equation. But you please, in order to get an exact answer, you please, if possible, write a code. Okay, that will give you a better idea. So there is a insulated rod of length 1 meter, and it has a square cross section. So basically, there is a rod. Okay, there is a rod whose cross section is a square cross section. The length of the rod is how much? It is 1 meter, and the length of the sides are 1 centimeter. So if it is 1 centimeter, so it is basically 0.01 meter. Okay. Now, cross section has its temperature fixed at 50 degrees Celsius at one end and 550 degrees Celsius at the other end. Okay. So here, say the temperature is 50 degrees Celsius, and on this side it is 550 degrees Celsius. So clearly we can see that there is a temperature gradient. If suppose this is the x direction, then there is a temperature gradient, right? Assuming steady state heat conduction in one dimension. So if it is steady state heat conduction, see, the heat conduction equation is del T by del T, where T is the temperature, alpha del 2T del x square. Okay, so if it is steady state, then what does it mean? This part is 0, or del 2T by del x square is equal to 0. And why I have written only one along x? Because it is one dimension in the question. Find the temperature at each node by finite difference method and compare with analytical solution. Divide the rod in 5 equal parts and take conductivity. See, whatever I have written here as alpha is conductivity, which is given in the question as K. Okay, so this is given. Now, del 2T del x square equal to 0. You have to take 5 divisions. Now, let us say this is the rod. Okay. How many divisions? You have to take divide the rod in 5 equal parts. So this is first part, second part, third part, fourth part, fifth part. So how many number of nodes are there? 1, 2, 3, 4, 5. There are 6 nodes, and you need to determine the temperature at each node. But for node 1, it is already given that it is 50 degrees Celsius, that is the boundary condition, and for node 6 it is 550 degrees Celsius. Okay, that is the boundary condition is given to you. Now how will you formulate? Is there any restriction given to you? Finite difference method. Now see, this is an elliptical problem. This is an elliptical PD. This is an elliptic PD, and for elliptic PD it is best represented by, if you have gone through the lectures, you must have seen that it is best represented by which type of differencing? Central differencing. Okay, it is best represented by central differencing. So how will you formulate central differencing? In order to formulate central differencing, see, T I plus 1 Ti plus delta x del T del x delta x square factorial to del 2t del x square. Okay. Similarly, ti minus 1 ti minus delta x del t del x plus delta x square factorial to del 2t del x square minus like this. Now here we'd like to preserve this delta 2t by del x square term. Okay, so if you'd like to preserve this, you simply add ti plus 1 with ti minus 1, so you will get twice ti. Okay, this will cancel out, then twice delta x square by factorial 2 is 2 only, del 2t del x square, so forth so on. We can neglect those things. Okay, so from here del 2t del x square is equal to ti plus 1 minus twice ti plus ti minus 1 divided by delta x square. Now what will be the value of delta x? See, the length of the rod is 1 meter and you have divided it into 5 equal parts. So when you have divided it into 5 equal parts, what is the value of delta x? It is 1 meter divided by 5, so basically 0.2 meter. Okay, delta x is known to you. Okay, now what you need to do is ti plus 1 minus twice ti plus ti minus 1 divided by delta x square is equal to 0. Now from here ti plus 1 minus twice ti plus ti minus 1 equal to 0. This is the system of linear equation. This is the equation that you will be getting for each node. Say for a node I, ti is unknown. Okay, you will start with node, you will start with C. At node 1 and node 6 it is already known, so you will start with node 2. So for node 2, if I write it, what will you get? Ti plus 1 means t3 minus twice t2 plus t1 equal to 0. t1 is known to you. Okay, t2 is the unknown, t3 is the unknown. Okay, so this is one equation. For node, similarly for node 3, what will you get? t4 minus twice t3 plus t2 equal to 0. Similarly for node 4, t5 minus twice t4 plus t3 equal to 0. Similarly for node 5, for node 5, t6 minus twice t5 plus t4 equal to 0. And for node 6 it is already known. So how many unknowns are there? Temperature at node 2, at node 3, at node 4 and at node 5. So there are 4 unknowns. How many equations are required? 4 equations are required. So you have obtained 4 equations. Okay, you have obtained 4 equations. Now once you have 4 out of this, t1 is known to you. Similarly t6 is known to you. Okay, you put the values. Okay, and then you solve this system of simultaneous linear equation to obtain the values of t2, t3, t4, t5. This is the answer. So this gives you a brief idea of what is happening. Okay, now if it is not steady state, in that case what will you get? There will be this additional delta t by delta t term will be there. So ti n plus 1 minus ti n, because it is parabolic, this particular term. Okay, time marching, divided by delta t. Okay, so what will happen? It will additionally increase the complexities, because you have to find for each node for all the time steps that is required to you, means all the time steps required to you. Okay, so basically you need to solve a system of equation like this for all the time steps, and the results of the present time step will be utilized in the next time step. Okay, so that is how it is done. So I hope this is clear. With this, let's stop here. We'll meet again the next week. Thank you.